continue. So we have defined now the nodes and the faces. We have here the picture from the nodes. Let us just concentrate then on the center control volume omega p. So we have then the capital W, capital T, and the capital E. We just focus on the faces defined by the midpoints. So then we said that this will be the xj minus 1, the xj plus 1. And we can now introduce the length of the control volume. So that would be then this length here. It will be delta xj. We shall also sometimes need the distances between the nodes. For example, between the distance between node P and node W is sometimes denoted by delta x from W to P, or the distance between the node P and the node E, sometimes denoted by delta x PE. So you see what is. And then we can now define the control volume omega p. So the control volume omega p is defined by, or it would be also the omega j. If we use the index notation, is defined by you see it here, that is our notation was that this is the lowercase e, this is the lowercase w, so that is then the x w to xe, which is the same in the index notation as xj minus 1/2 to xj plus 1/2. So that is the control volume, and we have the cross section is A, that we have already noted. It is constant. It was one of the assumptions for 1D, and the length of the control volume delta xp or delta xj. That is then the distance between the eastern and the western faces. And since they are defined by the midpoints, this is the same as the sum of these two. And that is then the same as, also the same as the average of the distance between these two. Of course, that would be the same, so we can also write it in this form. xj plus 1 minus xj minus 1, and that is the distance of the interval for the control volume j. So we have different notations here. So then we have defined our control volume, we have defined, and that is then at P, for example, we want to have then our unknowns. We assume that the averages are then located there. That was the first step 1, say the grid generation, essentially to say where do we have our unknowns, where do we have our faces, what are the control volumes and the distances. Step 2 is then the discretization using the finite volume method. And now, as mentioned before, we have to approximate the diffusion coefficient that is dependent on phi. And that is the first thing. If it is constant, we don't need that. That is easiest case. But the diffusion coefficient, if it is dependent on the unknown phi, then it has at each phase in the original equation 5 is approximated. And we do that the same way as we did for the heat conduction equation for the unsteady problem, either by the arithmetic or the harmonic mean. If we look just at the eastern phase, or if we just do that, just to concentrate here, to see the principle here, to see what is gamma E, the harmonic mean would simply mean that we take the average of gamma evaluated with the phi at P plus the phi evaluated at E. And that would be then in the index notation, it would be gamma j plus 1/2 is equal to 1/2 gamma j plus gamma j plus 1. And this notation here means, for example, the gamma p, that means that we have gamma of phi pi. So that is the meaning here when we write it in this form. That is the harmonic mean. If we would use the arithmetic mean, if we use the harmonic mean, then we would have the following. So these are approximations. I write it equal so that we have them directly. So it would be 2 gamma p gamma e divided by gamma p plus gamma e. The corresponding form for the index notation would be 2 gamma j plus 1 gamma j plus gamma j plus 1. And again, the index means function of phi j, for example, like we had there. So then, and the rule is the same as we discussed for the heat conduction equation. If you have a large variation from one cell to the other, then it is better to use the harmonic mean. Otherwise, you can use the arithmetic mean. In the same way for the W. For the W, it is then the average is then done, for example, for the arithmetic mean between the value of gamma in W and T. But we know that. So that is then regarding the diffusion coefficient, and the derivative that we need to approximate at each phase is the phi dx. So that is then in each phase in phi in 5 is approximated by central differences. And if we just concentrate on the eastern phase, then we would have the d phi dx at the eastern phase. So here, so if we have the values given at E and the values given at P, and we want the approximation, it is natural to take then the difference between the value in E and P and divide by the distance. So that would be then approximated by phi E minus phi P divided by the distance. And that is, this notation is now the distance we can write with this delta approximate delta form, delta x from P to E. So that would be the notation with the letters. The notation with the indices would be then j plus 1/2, and the phi E would be the phi j plus 1. That would be the phi j. And here we simply can take the distances, xj plus 1 minus xj. So then we have here our approximations, either in index form that we have here, or in with a letter form in this way. So then we can approximate by that the diffusive flux, having the diffusion coefficient and having the derivative. So here we have the diffusion coefficient with the arithmetic mean, and here we have the diffusion coefficient with the harmonic mean. Now we look at the source term. So the source term that is appearing in equation 5 is approximated by the following. What we need to approximate is the source average times the volume. That is essentially the integral over the source term S phi. And that is then approximated by a constant that is in the unchanged or uniform part of the source term. And we have some part that is dependent on phi itself. That gets SP phi P. So what we do here, we linearize the source term. So that is a major assumption here. So that is a coefficient. The SP is a coefficient. And phi p is our approximation of the cell average in the cell P. Now let us look at two examples to illustrate this approximation of the source term. The first is heat transfer. The heat transfer, now we model the heat transfer over the case of a rod. And the rod is at temperature T, and we assume that that is then, we have a heat transfer into the surrounding air. That is at a temperature T infinity. And we do that with this so-called heat transfer coefficient. And we call that H. So a heat transfer coefficient. And in the following way, first the idea that we have here is that we have again a pipe, circular pipe for example, and we are now interested in the heat transfer from the case. So here the case is then at temperature T, the outside is at T infinity. So we have a heat transfer. And then we model that by the following source term, that is then S of T, and that is then minus this heat transfer coefficient H times the perimeter. The perimeter for this example, so here we have the radius R, circular, so the perimeter here is then the length, if we go around the circle, that is then 2 pi r, and the area of this circular cross-section, that is simply pi r squared in this example. So we take then the ratio of the perimeter over the area and times T minus T infinity. So that is the model then of the source term. And the interesting thing is now what we get then for the SVP. That is the source. That is then in the steady heat conduction equation. We get in our case the integral from the western to the eastern face over this source term S of T, and we integrate then over, let's see, we integrate over x, but we have also the area to take into account. So we have the area, that is, so it's a volume integral. So this is then taking care of the x, and the area then is then taking care of that. We have the volume integral in the end. And if we do this here, we get here the integral over T. And that is our cell average temperature times the volume. And the volume is A times the length. So when we do this here, we get the H is constant, so there is no change. So there we get minus H, and then we have the A here that cancels with this A, so we get only the perimeter. And the length, we have already said that is the delta xp. And then we'll get here then the approximation of the cell average temperature in the cell P, and here we have T infinity. So then we can see what we have here. So we have then the heat flux over the case. And this here, the perimeter times delta x, that is the area of the case. Because this here is the delta xp, if this is here is the omega p. Because this is xw, this is xe. And the perimeter is then only where the heat can flow over the case. So that's the area of the case, and that's the temperature difference between the temperature in the rod and the temperature in the surrounding air. So then we have here the heat flux by modeled. So that is then the heat flux, the H, the heat flux, the heat flowing over the case per unit area, per unit time, and per unit temperature. So by that we model then the heat flux. So, and now we compute these individual parts, because we see here we have a part that is dependent on the temperature in the cell P and some part that is not. So we simply use what is left here, minus H times this gives us a plus. So we have the heat transfer coefficient times the perimeter. I write this circle in order not to confuse with our cell P. So that is then it is the perimeter times the delta xp times the T infinity. And then we have some other part that is depending on the Tp, that is this part here. Heat transfer coefficient, perimeter, delta xp, and the Tp. And now we can identify the terms in our source term approximation. And this term is then the uniform part Su, that is not dependent on the solution, it is just constant. And this part here, including the minus, that is the coefficient, Sp. And this here is then, in our case, the phi p. Our phi is the temperature. So then we have here an example of how the heat transfer of the case can be modeled by the source term. So that was one example, and the other example is then when we have a nonlinear source term. So that would be nonlinear source term. Term in the integral form of the energy equation. That would be equal to, let's see, I write it as a function f of Tp. And we assume that the function f is nonlinear. So that is a nonlinear function in this case. So what can we do? Well, that is what we do essentially all the time when we do the von Neumann analysis of a nonlinear problem, we linearize. So we do that also here. So we do a linearization. Around some guess. That might be an initial guess, or it might be an iterative solution in the iterative process we call Tp star. Because when we have a nonlinear problem, we need to do some iterations. We start with an initial guess, we do an iteration, and so on. Each time then we use, let's say, the latest guess to do this linearization. So that means we get the f of Tp is then approximated by f of Tp star, that is around which we make the linearization, plus the f prime, the derivative of f with respect to p at this Tp star. And that is then times the difference between the Tp and the Tp star. So that means we could do, say, a Taylor expansion around Tp star. And then you see that we get some term that is depending on the unknown Tp, which is the f prime Tp star at Tp, and we get some constant part, this, and f of Tp and f prime of Tp star times Tp star. So from that we get this. And as an example, let us take the following, that is the one from Tatanka. So we we assume that the nonlinear function is the following: 4 minus 5 tp to the power 3. So that is now our f of tp here in this example. Then we say that this is approximately equal to 4 minus 5 tp star. And then we have the f prime with respect to tp is minus 15 tp squared, minus 15 tp star squared. And that we have to multiply by tp minus tp star. So we are doing that, we're using this recipe here. And now we see we get here a plus 15 tp star. Here I forgot something. This is to the power 3. This is important. So here I forgot the power 3. Here we get minus 5 tp star 3. Here we get minus plus 15. So this gets 4, and then we get plus 10 tp star to the power 3. So that is taking this into account and this into account, and then we get here something left, which is minus 15 tp star to the power 2 times the tp. Now we can identify our source term approximation. That is the uniform part, and this is the coefficient, sp. And then we have the form that we assumed in the beginning. So that is then a linear approximation of the source term, what we do here. As we iterate, then we will gradually improve this, and then in the end, hopefully solve them the correct problem. So, now we have then approximations of the diffusion coefficient, of the derivative, and the source term. So they were all appearing in our basic integral form of the study 1, the diffusion problem. So now insert these approximations that we have now looked at of the diffusion coefficient, of the derivative, and of the source term into the basic equation 5. That then yields the following: 0. Then we have the gamma E using, say, harmonic or arithmetic mean, the area of the cross-section. Then we have phi E minus phi P divided by the distance between the corresponding nodes P and E. That is the diffusive flux at the eastern phase, corresponding diffusive flux at the western phase. Diffusion coefficient there times the area times the approximation of the derivative phi p minus phi capital W divided by the distance between W and P, and the source term approximation is then this linear approximation, uniform part coefficient SP phi p. Now we do. So that is what we get. And now we reorder this and get, so reordering following, that is then equation 12. And we do it that we collect everything unknown regarding phi p on the left. So let us start with that. So we get from here on the left, we get that with a plus. The coefficient is gamma EA divided by this. So gamma E divided by the distance, delta x PE, times the area, times phi p. Then the part from here regarding phi p on the left hand side gets also with a plus. So we get the diffusion coefficient of the western phase divided by the distance between the western and the centered node times the area. And then we get also this coefficient from the source term on the left hand side with a minus, SP. And that is all multiplying then our unknown quantitative cell P. And on the right hand side, then it stays following. Here we have the phi E. That is then I start with the gamma west. So minus gives plus, divided by the distance between W and P. Area, and here we have then the phi capital W. Now the E term is then next. Gamma E divided by the distance between P and E times the area, that is phi E. And then there is this uniform part of the source term SU left. So then we have this equation, and then we use the notation by Patanka to identify these coefficients. The coefficient in front of the center of the unknown P is this coefficient that gets the coefficient A capital P. Coefficient in front of phi W gets the coefficient A capital W, and this gets the coefficient A capital E. So then we get from this, by this identification of coefficients, the following equation, that is then equation 13, AP times our unknown phi p is equal to AW phi W plus AE phi E plus the uniform part of the source term. So that is the equation that we get, and we have then these coefficients as they are defined here. And the interesting thing with these coefficients is, and it will repeat when we get also to 2D, that the AP is built up of AW and AE. You see, this is AE, this is AW. So let us note that. So if we write now these coefficients, then we'll find that the A capital W, we have already done it, but we repeat it here for having them clearly identified. So the AE is the gamma E, so this is a lowercase w, lowercase e, distance between the nodes P and E times the area. And now the thing what I said was that the AP is built up by these. So it is AW plus AE minus the source term coefficient SP. And that is typical. So then we have the letter notation with capital P, W, and E. But we can also write this in form of the index notation. So equation 13 corresponds, to use now the index notation, that would be then 14. And now I take the freedom to move these to the left-hand side. And then I introduce then the following notation: Bj phi j minus 1 plus Aj phi j plus Cj phi j plus 1 is equal to Dj. And this is true in our notation for 2 to nj minus 1.
Excuse me, what's that one coming from? AB equal to AW.
Where are you?
Second line.
This line?
Mm-hmm.
This here?
No, because is that the same as 13?
We are discussing this.
Ah, okay.
Okay? So now we are discussing 13, and then we make this identification that we say what are A, B, and C, and D. So in this notation here, we use then the following. The Bj, as you see here, is then coming from the minus AW. And if we would write that in with the index notation, it would be minus gamma j minus 1/2 divided by xj minus xj minus 1 times the area. The Cj would be the minus AE, which is minus gamma j plus 1/2 xj plus 1 minus xj times the area. So I'm translating now these coefficients to the index notation. And the Aj, that is then equal to, it's equal to AP in the first place, and then it is equal to minus Bj plus Cj plus Sp. And that is then, well, we can identify then all these terms, so it is these terms with a plus and this with a minus. And that would be then the Sp, let's see, I can also replace that by the S, could also be, so that would be then the Sj, if we want to identify that. Okay. So, then we have simply introduced other notation. So, and by the advantage of this is, we see now that these coefficients that we have here, AW, AE, and also the AP, they are not the same. If we have varying situation for the gamma, for the lengths of the intervals, then these coefficients will change. And that is better reflected with the index notation, because there every index has its own value, and they don't need to be equal. So the thing that we are going to discuss tomorrow is how to introduce boundary conditions with that. They have not yet been taken into account, so we'll do that. And you can already guess from this form here that we will get in the end a tri-diagonal linear system. That is what we end up with. Okay, so we stop here. Yes?
What about Dj? Is it SU?
Thank you for that. Yes, I've got that. Thank you. So that we need. Good point. So the Dj is SU. Thank you. And also there, that might vary. Okay, so then we are.